Hello, I am Paola Saccomandi, professor at Politecnico di Milano in Italy. In many hospitals today, thermal therapies like radiofrequency, microwave, and laser ablation are widely used to destroy tumors by raising tissue temperature. But they come with a critical challenge. Temperature must be measured accurately and in real time. A few degrees Celsius can make the difference between complete tumor destruction and damage to healthy tissue. Thus, having a system that can precisely measure the tissue temperature change and control the therapy is still a dream. Today, I'll focus on how fiber optic sensors and optical imaging are reshaping temperature monitoring during thermal cancer treatments. Let's start with the problem. During thermal ablation, tissue temperature can exceed 80 or even 100 degrees Celsius in very localized regions. At the same time, just a few millimeters away, critical structures must be protected. Traditional temperature sensors like thermocouples or imaging-based methods often struggle in this environment, suffering from electromagnetic interference, artifacts, or limited spatial and time resolution. This is where fiber optic sensors come in. Fiber optic sensors are very thin, flexible, and immune to electromagnetic fields. They can be inserted directly into the tissue alongside ablation probes without disturbing the therapy. Among them, fiber Bragg grating sensors, or FBG, are particularly powerful. An FBG is a microscopic grating structure written inside the core of fiber that reflects light at a specific wavelength. When temperature changes, the reflected wavelength shifts linearly with temperature. By measuring this shift, we obtain highly accurate temperature readings with sensitivity around 10 picometers per degree Celsius. But the real strength of an FBG is its spatial resolution. Multiple gratings can be inscribed along a single fiber, creating a chain of sensing points separated by just 1 millimeter or even less. This allows us to capture the steep thermal gradients generated during ablation, which can reach tens of degrees Celsius per millimeter. Using sensors with insufficient spatial resolution can lead to dramatic temperature underestimation, sometimes by more than 10 or 15 degrees Celsius. And that's not a small error when patient safety is involved. Because of their reliability, fiber optic sensors are now used not only to measure temperature but also to control therapy. In closed-loop systems, the power of the heat source can be automatically adjusted based on temperature feedback from FBG sensors placed inside the tissue. This transforms thermal ablation from a pre-planned procedure into an adaptive sensor-driven treatment. Fiber optic sensors have also proven essential in photothermal therapy, where nanoparticles are used to enhance heat generation inside tumors. With multi-point FBG arrays, we can measure temperature at several locations inside the tumor at the same time, quantify thermal enhancement, and compare different laser wavelengths or nanoparticle designs. In short, these sensors allow us to see what was invisible before: the internal thermal landscape of tissue during therapy. Optical sensing doesn't stop at fibers. A complementary approach is hyperspectral imaging, which uses light reflected from tissue to detect temperature-related biochemical changes. While it doesn't replace internal sensors, hyperspectral imaging can provide surface maps of thermal damage, offering valuable information during treatment. Together, all these technologies point toward the future where thermal therapies are guided not just by images and by the experience of the clinician, but by dense real-time sensor data. Fiber optic sensors are small, precise, and immune to harsh clinical environments and are becoming a cornerstone of safe and effective tumor ablation. By embedding intelligence directly into the treatment zone, these light-based sensors are helping clinicians deliver the right dose of heat exactly where it's needed and nowhere else.